Hi, today I am going to explain about the quinolone antibiotics. These quinolone antibiotics are used in the treatment of bacterial infections. Um, the mechanism of action of these quinolone antibiotics is they inhibit the bacterial DNA gyrase. DNA gyrase helps in the unbinding of the DNA and subsequent DNA replication is hampered. So these quinolone antibiotics they bind particularly to the DNA gyrase, and in that way it acts as a bactericide. So before talking about the these quinolone antibiotics or fluoroquinolone antibiotics, I'm going to talk about the nalidixic acid. Though it is a naphthalidine molecule present here, but it is very similar to the quinolone antibiotics. This is considered as the first generation antibiotic in the quinolone category, though it is of course having an naphthalidine nucleus, but the structure is very similar to quinolone. This is a naphthalidine nucleus, and at the first position there is a ethyl group present here, and at the third position you can find the carboxylic acid group, keto group here, and a methyl group present here. This was considered as the first medicine to act on the DNA gyrase at the times, and later on the quinolone antibiotics have come with the fluorine group attached that is called fluoroquinolones, and they designed these structures in the different molecules have been designed in the fluoroquinolones based on the similar pattern here. I'm going to explain about the fluoroquinolone structure now. Now this is the fluoroquinolone antibiotic. This is Levofloxacin. Here the fluoroquinolone itself indicates that there is a fluorine group attached here. Unlike in the nalidixic acid, we don't find the fluorine group attached. In the nalidixic acid, you have a nitrogen group attached here. So that's the naphthalidine moiety that is absent here. This is a quinolone moiety. This structure would be present in all the quinolones. This is the quinolone moiety, and the carboxylic acid is exactly present there. The keto group is present here in this way, and in the norfloxacin molecule, the ethyl group is present here. In the nalidixic acid also we can see the same position. The fluorine group is just attached, and at this position, previously there was a methyl group in nalidixic acid. Here the piperazine molecule is attached. So this is the norfloxacin molecule. So for this, I'll attach a cyclopropyl ring here. I will remove this ethyl group in the norfloxacin. This is a cyclopropyl ring. I will attach this one to this at this position. So at the first position of the nitrogen, I have attached cyclopropyl ring. So this becomes ciprofloxacin. The word ciprofloxacin means that the cyclopropyl ring is present. Cyclopropyl. So this is ciprofloxacin drug. Now I will do one thing. I will remove this thing. I will remove the cyclopropyl ring. I will attach the ethyl group again back. I will attach the ethyl group back again, and then here, previously I was not attaching the hydrogen bond here. Now here I will attach one more fluorine atom here, and then at this piperazine moiety, here at this position, I'll attach one methyl group. I'll attach one methyl group. Okay. Now this becomes Levofloxacin. This molecule has two fluorine atoms. This fluorine atom is not changed. This is always present in every molecule of the fluoroquinolone. And at this position, I have attached one more fluorine atom, and to the piperazine ring here, I attached methyl group here. So this becomes the Levofloxacin. Now I will prepare ofloxacin. Ofloxacin has a benzoxazine moiety attached. Benzoxazine means there is an oxygen and nitrogen in the benzene ring. So forget about this. This is okay. I will remove this one. This is benzoxazine moiety. One oxygen and one nitrogen is present. So to this benzoxazine moiety, I am attaching one methyl group here, and this will bind here. So these three I will remove. I am removing these three. So I am attaching here like this. And to this I am removing the methyl group here, which was actually present in the Levofloxacin. I am attaching this methyl group to the nitrogen position. So NCH3. Now this becomes ofloxacin. Ofloxacin has the benzoxazine moiety along with one methyl group, and previously we saw in the piperazine moiety this methyl group is not attached to the nitrogen, but in this ofloxacin we can see there is a methyl group attached. And ofloxacin and levofloxacin are almost the same. Both these two are very similar. These two are same in structure in the 2D form, in the 2D format. But except at this position, this is the normal ofloxacin. This is ofloxacin. In the levofloxacin, this becomes an S enantiomer. So that is why it's called as levofloxacin. So the levofloxacin is present as an S enantiomer in the plasma also. Even it doesn't change to the ofloxacin derivative even after 48 hours of after the patient has taken the levofloxacin. So it is the main unchanged. The whole drug is unchanged, and it has better efficacy. So that's the difference between the levofloxacin and ofloxacin. It's just the stereochemistry here. There is S enantiomer. That is, S enantiomer means it is present towards the plane. The methyl group is attached towards the plane. Now I'll make fluoroxacin. I'm removing this benzoxazine ring, and I'm again attaching a fluorine molecule here, fluorine atom here, and attaching ethyl fluoroethyl group. I'm attaching a fluoroethyl group to the first position. Okay. Now this becomes fluoroxacin. It has a fluoroethyl group present here and one fluorine atom here. The piperazine moiety with the methyl group attached to the nitrogen atom is not changed. Only these two changes have been made. So it has a fluoroethyl group, one fluorine atom extra. So in this fluoroxacin we have a total of 3 fluorine atoms. If you see in all the structures, we are not changing the carboxylic acid group and this keto group. This structure is not changed at all. Even this. Only the changes have been made in these places. Now I will make the perfluoxacin. I am removing this fluorine atom and replacing it with the hydrogen, and now I am removing this fluorine atom here also and replacing it with the hydrogen, and now it becomes perfluoxacin. The perfluoxacin and the fluoroxacin are almost very similar, except the fluorine atoms are replaced in the fluoroxacin, and here in the perfluoxacin the hydrogen atom is present. Okay, it's fine. And I'm going with the last drug, nadifloxacin. Nadifloxacin has the structure very similar to this. Until now we have seen the piperazine moiety attached here, but in the nadifloxacin we can see the piperidine ring attached. So if the piperidine ring has one hydrogen atom in the benzene ring, in the 6-membered ring there is one nitrogen atom. So I have to remove this nitrogen here. To this piperidine ring, I am attaching a hydroxyl group. The hydroxyl group is present to the piperidine ring. To the nadifloxacin, I have made changes in the piperazine ring. It is replaced by the piperidine ring attached with a hydroxyl group, and here I am attaching a benzene ring here. So I will attach a benzene ring. This is the structure of nadifloxacin. It has a benzene ring attached here. We need to change the bonds. This double bond. So if we look at the bonds, we need to change the orientation of the bonds here. But this is the structure of nadifloxacin. So in all these fluoroquinolones, there are several other fluoroquinolones like jatifloxacin and many other, but all share the common characteristic of the quinolone ring. These two they don't change, and the carboxylic acid group and the keto group and the fluorine group. So thanks for watching the video. Please subscribe.